Welcome to Spring LIB.
Right. In this question, we are engaging in some relativistic space travel, and we want to know, given a destination to a star, the time that it will take the spacecraft as measured on Earth and on the craft. What's the distance the spacecraft travelers think they went? And then do they compute their speed to be? So the first thing we need to do is take our distance, L naught, of 21.6 light years. That is a distance, friends, and we need to calculate it in meters. How do we do that? Remember that a light year is the distance that light travels in 1 year. So we can take its speed in meters per second and then multiply by the number of seconds in a year. And so I'm going to take 365 days, and then I'm remembering that there are 86,400 seconds in a day. You can look that up if you don't believe me. And multiply, so that speed times that amount of time gives me a distance in meters, but then multiplied by 21.6 because there are multiple light years. And that gives me 2.0435 times 10 to the 17th meters. Next, let's take a look at that velocity, which is 0.95 c. In some cases, it's going to be appropriate to use it as is, but we may need to, in fact, we will need to compare in a number of meters per second. So we'll get 2.85 times 10 to the 8th meters per second. Now we're ready to dive in to these calculations. So how long will this seem to take to observers on Earth? Well, that quantity is delta t, and that can be found with L naught divided by V. So we will take 2.0435 times 10 to the 17th meters, and then it's up to you whether you want to plug this in as 0.95 times 3 times 10 to the 8th, or just go ahead and use that 2.85 times 10 to the 8th. And that gives us 7.17 times 10 to the 18th seconds. And again, dividing that by 365 times 86,400 tells me that that looks like 22.74 years. Just because we want to be able to compare nicely. Well, great. Now let's take a look at the time on the spaceship. That's delta t naught. And we can find that with delta t multiplied by the factor of 1 minus v squared divided by c squared. And I am going to, in this case, so 10 to the 18th seconds, I'm going to write this as 0.95 c quantity squared divided by c squared, because now the c squareds cancel, and I get 7.17 times 10 to the 18th times the square root of 1 minus 0.95 squared. So you see how that simplifies and makes it a little bit easier to plug into the calculator. And I got 2.239 times 10 to the 8th seconds. I am so sorry. I just realized that it's 10 to the 8th seconds above, not 10 to the 18th. Oh my goodness. I was wondering why that seems so far off. That should be 7.17 times 10 to the 8th, which means I need to go through and fix it everywhere. Yeah, I have it correct in my notebook, but here I am looking at my screen instead. Hey, there we go. So now we can calculate how far does this appear to be for our spacecraft folk, and that's going to be a length contraction. So we'll take L naught times 1 minus b squared over c squared, and that gives me my 2.0435 times 10 to the 17th meters times the square root of 1 minus, once again, I'm going to do 0.95 c, the entire quantity squared, divided by c squared. And that gives me that same, I'm just going to go ahead. That gives me that same factor of the square root of 1 minus 0.95 squared. I'm just going to go ahead and cut straight to the result here, which gives me 6.381 times 10 to the 16th meters. And now we're asked in part D, how fast do our spaceship folks think they're moving? And so we can find, I'm going to call it V naught, we can find with L divided by delta T naught, which gives me 6.381 times 10 to the 16th meters divided by 2.239 times 10 to the 8th seconds. And that gives me 2.85 times 10 to the 8th meters per second, which is the speed that they're traveling.